Hello everyone, my name is Aaron Standard. I'm the founder and CEO of Petabridge, and today we're going to go over part 2 of my video series on high optionality programming. So if you missed the first video, you should go back and watch that, where we introduced the concepts that comprise high optionality programming. In this video, we're going to go ahead and talk a bit about how to actually implement it. What are some of the specific techniques you can use to reduce the amount of exposure to technical debt you have over time as your systems evolve, and why do these techniques help you achieve that? I'm going to try to answer those today in this video. So I'm going to go ahead and begin where we ended our last video by talking about the list of techniques that can help give you options for reducing technical debt down the road. The biggest one conceptually is event-driven programming. We have an entire playlist that's dedicated to our event-driven distributed architecture series. I'd recommend checking that out. We're going to start by exploring that and how that helps reduce technical debt. Likewise, event sourcing and CQRS are two techniques around persistence that tend to complement event-driven programming very nicely. We're going to talk about how those help reduce technical debt and increase optionality as well. And finally, we'll talk about actors and extend-only design. These are all programming techniques that aren't silver bullets per se, but they're tools that when you use them the right way can help give you some flexibility in how to introduce changes into your system in the future. But they come with a premium, which is that these aren't as simple as, let's say, coding directly against a database or using really simple patterns like repositories, for instance. These patterns are a little bit more architectural and require a bit of a learning curve, and they require you to consider how to go about implementing certain parts of your domain a little bit more carefully than you would if you just dove right into defining controllers and views and all that sort of jazz. So there is a premium to be paid upfront for implementing these. My job in this video is to explain what that is and to show you what the potential payoff might be at some point down the road, and talk about how these techniques can help you mitigate these evolutionary pressures that are going to drive the need to evolve your system. And normally it's the paying of that technical debt occurs then when that evolution occurs. We're going to see if we can reduce that cost by making some better design decisions earlier. So let's start by talking a bit about event-driven programming. So in the context of thinking about optionality, it's important to contrast event-driven programming with the other practices it replaces in effect. And the number one practice it really replaces is the sort of procedural style of programming, thinking about methods and return values. The distributed version of this, of course, is remote procedure calls or web APIs, where you're essentially thinking in terms of function invocations all the time. With event-driven programming, you're really thinking about messages, where a message can contain an event, it can contain a command, or contain a query. And there's differences between all those different message types there, but fundamentally, all messages can be serialized, they can be sent over the network, and each message input might be responded to with between 0 and n message outputs. And so there's a lot of flexibility built into how message passing can be implemented compared to our RPC sort of method invocation style. When a method's invoked, you have to return a value. You can await on it, but ultimately you still need to return something eventually. Whereas with message passing, it's much more flexible in terms of the different models we can use to try to execute this. So for instance, all messages typically comprise of two parts: a payload, which has your domain sort of data inside of it, and then a reply to address. In Akka.NET, this reply to address might be an actor reference or an actor path. In a system like RabbitMQ, maybe it's a reply to topic that you need to reply back to. The way these are implemented can vary, but the concepts are the same across most of these event-driven systems. But the advantage of this is that this allows us to make all message passing and all event-driven programming inherently asynchronous. As long as I have that reply to address, I don't need to reply back to it right away. I can go ahead and send it a message at a much later point in time if our protocol allows for it, if I want to. You already get a lot more flexibility than you do with sort of, let's say, method calls, where I have a caller waiting on my return value and I'm blocking its flow of execution until I send something back. Event-driven programming, by its very nature, is non-blocking by default. It's always asynchronous. So I send a message and I don't necessarily have to wait for a reply to come back. I can move on to do some other piece of work instead. This gives us a lot of flexibility around how we essentially handle workflows and all the other types of activity inside our system. Now, the other big advantage of the way messages are designed is that they lend themselves very well to serialization. Essentially, a message is an artifact that we can persist into an append-only log, like Apache Kafka or Akka.persistence if we want to. Or we can go ahead and just keep that event in memory and just pass it on right away without serializing it if we don't want to. But the fact that we can serialize it allows us to do all sorts of interesting things with it. A good example, one way you can do regression testing on complex applications. So for instance, the way a lot of our customers who build machine learning applications on top of Akka.net do testing is they'll go ahead and keep a log of all of the events that were fed as inputs into their model. And they'll also record another set of events that were outputs that were emitted by that model. They'll go ahead and redesign the model. They'll rerun the original events against the new model, and they'll be able to compare how the two approaches worked. This is very popular for things like algorithmic trading, for instance. We have a lot of customers that build things like foreign currency or equities trading algorithms inside Akka.net. Being able to serialize and replay events using something like an event source, which is the next concept we're going to introduce, gives you a lot of flexibility to test what are the real impacts of the changes you're going to make. And the more complex your system is, the more valuable this becomes. So having this sort of event-driven way of reasoning about the history of your system is extremely useful from that point of view. And we'll cover that a little bit more in the next section. Now, the other big benefit of events is that you have the ability to manipulate the order in which they're processed. So events are produced whenever they're produced. But there might be a lot of situations where you can't process certain types of events right away. A good example of these are state machines. That in order for you to process input B, you need to wait for input A to arrive first, because that is a critical piece of data you need in order to successfully compute the command that's sitting inside, let's say, message B. You have the ability using things like the message stash in Akka.net to buffer that message until message A arrives. Then you can unbuffer it and process it, send the response back. It gives you a lot of ability to regulate the flow of activity inside your system. Whereas in a traditional RPC system, you have to process everything simultaneously because it's all designed to be fundamentally stateless. There's no real notion of having, let's say, state machines inside an ASP.NET controller. You can only really get that through a stateful sort of event-driven processing system like Akka.NET or like technology like N-Service Bus Sagas, for instance. So the ability to go ahead and order and reorder events allows us to create deferrals. The ability to go ahead and defer processing to another until another event arrives. Finally, we also have the concept of delegation. This is not something you can do very easily inside traditional procedural programming. The way delegation looks like there is polymorphism and inheritance, or possibly doing composition, where you have one class receives a method call, and it's able to go ahead and forward that method call down to, let's say, another implementation. But this is all happening in process, and it's happening right now. It's effectively synchronous from a flow control point of view, even if you do have await statements in there. In a message-driven system, we have the ability to add location transparency and the ability to go ahead and delegate messages to completely different parties than other than the one who received it. We use this inside Akka.NET for routing quite heavily. And the reason why this works is because of that reply to address. Let's say the client who is waiting on this response to its message does not care who sends it the reply back. It just cares that it gets the matching reply back to its request. Or if we're building a stream, we go ahead and care that we get the stream of replies back. We don't necessarily care who sends it. That's not something you typically assert in an event-driven system. So that creates the possibility of being able to delegate work around, which means we have the ability potentially to move parts of our system between deployments without breaking any of our messaging systems that are currently in place. This gives us quite a bit of flexibility when it comes to refactoring down the road, and is a very powerful option that gets used quite heavily as you start, getting larger and larger, let's say, services, and you want to start thinking about breaking them up for some of the standard microservice reasons. Good example would be hardware and resource isolation, where you want to make sure really busy processes are kept physically separated from processes that contain critical state. You can go ahead and use the forwarding and delegation patterns that event-driven programming affords to safely introduce that change without it being a gigantic high-risk job. That's one example of high optionality being introduced there. Finally, the last really big benefit of events is multicasting, or broadcasting might be a better way of putting it. The ability for multiple parties to all receive and process the same message. So for instance, using a event sourcing system, I can go ahead and have multiple different listeners take the events from one entity or from one tag in something like Akka.net, which is a way of being able to group events together from multiple entities. I could have someone go ahead and listen to those events and project them into totally different forms than what my original domain model was using them for. This can be really useful for producing things like reports or indices, or being able to perform other types of, let's say, non-domain operations, such as monitoring, for instance. So there's a lot of power that can be added to your application by introducing event-driven architectures as a first-class citizen. Now, the downside of this is that event-driven architectures require a lot more planning in advance. They require you to go ahead and build a grammar of events and messages that can be handled by your application, and they require you to have some way of serializing, persisting them, and replaying them. That's actually a fairly significant amount of infrastructure if you don't plan it well. And in particular, it can be tough to go ahead and choose what are the right ways to go ahead and model domains and events if you've never done this before. So there is a bit of learning curve to it there. Now, in terms of some of the interaction patterns, I've given some examples here. This is from some of our typical Akka.NET presentations of different ways you can go ahead and interact between different, let's say, objects, or possibly even different services inside an event-driven system. You have a broadcast style where one node emits an event via fire and forget messaging to many others. You have proxying, which is a standard type of delegation pattern. And then finally, you might have something like publish and subscribe, where a message arrives at a subscriber node, and it goes, at a publisher node, and it publishes those messages back out to multiple subscribers, who can in turn do some work with it and then maybe publish events to their own subscribers downstream. And then we have, of course, one-way messaging, otherwise known as fire and forget. Well, the way that all those patterns really go about reducing our exposure to technical debt and increasing optionality is through all of that flexibility I just showed you. They give you many different ways of dynamically replaying existing messages that might have been event sourced into your system, which is the next pattern we're going to talk about. Or they give you the ability to go ahead and flexibly kind of reroute messages inside your system in response to things like traffic conditions, network failures, or possibly even during deployments when you're just introducing or refactoring. The fact is that event-driven systems tend to lend themselves very well to properties like location transparency, which gives you the flexibility to move where work should happen relatively easily inside your system without breaking all of the different code that depends on where that work was happening before. It's much more decoupled in that sense than a traditional RPC system is. So this gives us a lot of, let's say, inbuilt protections against some of the normal refactoring pain that would come into breaking apart our application into smaller services down the road. These event-driven systems, through their very nature, already give us a lot of good built-in tools for being able to do that. Now let's talk a bit about event sourcing as sort of the next technique for helping mitigate some of the technical debt pressure that can build up in an application as it evolves over time. So I'm using Akka.Persistence as an example here. This is a event sourcing module that's built into Akka.NET itself. And the way it works is that actor state is always resident in memory. That's the entire point of using actors. You want to have this low latency messaging experience. So in order to do that, you need to have a local state in order to achieve it. Well, as these messages are processed by my room message history actor here, I'm going to go ahead and build up my actor state. And that's going to contain the chat messages that are being saved into this chat room here. And we're going to persist those messages asynchronously to SQL Server in a append-only table that Akka.Persistence maintains for me. And when queries come along to go ahead and request data from the room message history actor, we're going to send them copies of our in-memory data. We're not going to query the database in order to do that. This is just an implementation detail of how Akka.Persistence works. If my process crashes, or if I move this actor from one node to another during, let's say, a deployment or rebalancing, which is something that Akka.NET will do periodically if you're using Akka.Cluster sharding, what will happen with this actor once it gets moved is it'll go ahead and query SQL Server to figure out what was my highest sequence number, which is essentially it's a monotonic counter that indicates the version of your state. It'll say, get me my highest sequence number. It'll get that value, and it'll go ahead and replay all of its messages that are stored in the journal until it gets complete state recovery. So everything that was persisted previously in the journal has to be rebuilt in memory in order to allow this actor to do its job. So this is kind of the basic tenets of what event sourcing looks like as it's implemented in Akka.NET. How does this help us with optionality? Well, the current state is the sum of past events. This introduces a very powerful option, which is that your current state of this object can always be changed by replaying previous events using new event handlers possibly, meaning the events themselves are immutable. Their meanings can't be changed. But the way we project those events into business state can always be changed safely without compromising what that past history means. And that's what I mean by option number 2 here. So option number 1 is state can always be rebuilt. So if you're using, let's say, snapshots in Akka.net, those snapshots are synthetic. As long as you're not going back and deleting the original events you persisted, you could always blow away all those snapshots and have your actors perform a full recovery, and they can go ahead and rebuild their entire application state from scratch that way if you want to. Now, the second powerful option is you can always change the way state is built without changing the events themselves. This might allow us to go ahead and safely introduce new models or new views of that original data that was there without changing the data that was there in the first place. This means that we're not risking essentially modifying the history of what happened. We're simply changing the way it's presented upstream to, let's say, our end users or possibly through our APIs to other parts of our software. That's an extremely powerful component because it allows us to start doing things like I mentioned earlier, simulations or predictions or regression tests. The way, for instance, big game studios like Blizzard regression test massively multiplayer online RPGs, games that are far too complicated to be essentially tested using simple unit tests, is they typically take a append-only log of events from real players, like a saved game scenario, and run that over the new version of the software, and they look for critical regressions that might have happened, or they look for how the outcomes might have been different had the, let's say, the game engine implemented this rule versus this one. So this is a really powerful set of tools for allowing us to safely introduce changes in the way we handle state in a way that doesn't threaten our ability to retain our old history. The biggest risk in any, let's say, major refactoring is accidentally destroying old business data that you still need. Good example, if you're trying to move between, let's say, payment processors, if you're building an e-commerce platform like the type we've built with SDK Bin, if you manage to somehow enter into a state where you couldn't use any of your old, let's say, Stripe subscription objects you created before, and there was no way to go ahead and essentially restore those without having the customer have to go ahead and create brand new ones all over again, you could risk losing tons of revenue. And if you think that sounds far-fetched, it happens all the time. It's the sort of mistakes people make when they aren't careful with their historical data and what the meanings are. Event sourcing is a really great technique for being able to avoid a lot of those problems because the source of truth is always these immutable events whose values can't be changed. And we'll talk a bit about how to version those events using extend-only design. Again, I've got a whole dedicated video we just built that talks about how to do that safely over long periods of time and many versions of the software. But event sourcing is inherently a lot safer than what most developers use, which is object stores, essentially, where you go ahead and take a C# or a .NET object and you model it as typically a single row inside a database, or in some cases, maybe multiple rows, and you use something like an ORM to try to map it back. Whereas with event sourcing, the objects themselves are inherently versioned. You can always see why they were changed, and you have the ability to go ahead and rebuild that object in different ways without necessarily changing what those events are. So it's much safer and ultimately provides you a much higher degree of optionality than the object store methodology does. Finally, the biggest benefits are that you can introduce new event types without modifying prior ones. Schema is not shared in an event source system. Each event has its own independent schema. And when you go ahead and modify one event or introduce a new one, it's not going to have, let's say, cascading side effects on the others. When people try to model, let's say, event-sourced systems using table schema very strictly, if you go ahead and modify a column or drop a column, that's going to affect all rows in the table. And that could be a pretty catastrophic change if it's not done correctly. One of the things that event-sourced sort of designs tend to lend themselves to is events are usually serialized as either binary or JSON, and usually the payload inside, let's say, a system like SQL Server will offer some instructions on how to deserialize it back, typically using something like a manifest, which is basically just a way of representing here's the concrete type that this can be deserialized back into inside the application. That's how Akka.NET serialization works, for instance. What you can basically do is make sure that if you're using a schema-based approach like that, any individual event's type isn't shared with any of the others through some shared common schema like SQL Server. Usually they're all defined independently inside something like a protobuf file, or maybe you have a mapping system that's able to use reflection, or maybe it's going to use a source generator to go ahead and translate a CLR type into an event type inside some SQL database somewhere. Being able to introduce new types without having side effects on other ones helps increase the safety of the system over the long run and makes it much less likely you're going to introduce an irreversible regression that's going to blow up your system. And so finally, the other big benefit of event sourcing is that it typically doesn't rely on database-specific features, so you can meaningfully abstract it. Akka.persistence is a very good example of this, for instance. Akka.net does not rely on a lot of database-specific features in order to work. We basically need keys for being able to look up events that have a specific entity ID, and then we need to have some way of computing the range of different sequence numbers that belong to that entity ID, and that's it. Even simple key value stores can make that pretty easy. We don't need some complex SQL query or a full text query to make that work. So event sourcing really helps simplify and reduce your dependence on a lot of database-specific features if you want as well. That's why at Petabridge, we typically use Azure Table Storage for doing this. We want something that's very simple, something that's very inexpensive and large scale, and we don't need a lot of bells and whistles out of our database to do it. So we use Azure Table Storage to do that. Now, if we need to go ahead and materialize event source data into an index that can be searched, this is where CQRS enters the picture. CQRS is a concept that has been around for about 10 to 15 years now. And what it boils down to is that your read and write models should hopefully be separate. So in the before state, we would have our presentation layer, validation, business logic, and then we'd have a generalized data access layer that would have both the combination of reads and writes inside of it. Whereas in a CQRS approach, and I've borrowed this diagram from Microsoft's own documentation here, in a CQRS approach, we basically go ahead and have a separate read and a write model. Our write model is responsible for validating commands as they're received and then turns them into events that can be persisted. Now, CQRS does not strictly speaking depend on event sourcing, but they often get used together. The idea behind the read model is that it's able to go ahead and use the data that's been persisted, and it can project it into different views that themselves might also be persisted. That's sort of what a materialized view is in CQRS. So it's the idea of that your read and write models can be different, even though the data that's being written is kind of one and the same. This helps free up a couple of different sticky notions that developers sometimes get themselves into, which is namely that they have to fit all the requirements on the same domain model, or really it's on the same write model. And that's very labor intensive, and that's what leads to all sorts of crazy database driven development where you have stored procedures that have 1,000 lines in them and things like that. Keeping the two domains somewhat separated, your reads and your writes from each other, helps simplify that quite a bit and gives you the ability to write in the fashion that's best for the write model, and then the read model can project what it needs based on what was written. CQRS is often used with event sourcing. And the way it typically gets used in event sourcing is that the read models will go ahead and subscribe to the events that are being written. And based on those events as they arrive, it will materialize a view of some type that can be accessed directly via a query. So for instance, one thing we might do, let's say we're using Azure Table Storage for event sourcing all this data from all these different entities. I might go ahead and have an Akka.persistence query. That's how we do CQRS in Akka.net. We might have an Akka.persistence query that's listening to those events as they're being written for a specific entity, or maybe we might use a tag, which is like a secondary index in Akka.persistence. We might go ahead and read based on one or more tags or one or more entities and try to create a projection. And that projection might be building something like an Elasticsearch index, or maybe we're just going to insert rows into Postgres. And we might go ahead and power some queries in our web UI using those Postgres rows we're generating. So those read models are effectively synthesized from your write models, and this allows us to update them independently. If I want to improve the way my read model works, I can do that without having to touch my write model, which gives me a lot more flexibility and a lot more ability to change either without necessarily having side effects on the other. The other big benefit of doing this is that you can tune the performance characteristics separately for read and write models. Good example, if I have a super high throughput read-oriented system where I need the ability to get notified about, let's say, real-time updates to something like a stock ticker price, and I still want to use event sourcing as part of my design there, where I go ahead and I persist the event, and that persist call might also cause that event to be written to something like a Redis topic, or maybe a Azure Event Hub topic. And then on the other side of the network, my read model can get that event right away, and it can go ahead and use it to create a projection. And that projection might be a volume-weighted price if I'm doing stocks. Or maybe that projection might be a notification that my trade indicator has fired. Depends very much on the model that I build. But the other really big benefit of this is that I can have several read models all subscribing to the same events. Meaning that I can go ahead and have, let's say, hundreds of different subscribers who all want to know about these events that are being written for one ticker symbol on my stock trading sample. And I can always add new ones or remove old ones without having any impact on the right side of that system at all. It's my infrastructure for being able to go and propagate those events via my sort of my choice of CQRS implementation that's responsible for making sure data gets from point A to point B. I can always add new models and deprecate ones that aren't being used anymore with basically zero cost to my right side. That's a huge advantage of CQRS. The other big benefit of this, like I mentioned, is that read and write models can use totally different database instances or technology. So this gives us quite a bit of flexibility from an implementation standpoint. We don't really want to try to manage, let's say, whether or not a customer's account is paid in full or by having to go and replay the entire history of their payments all the time. We'd rather have a CQRS system that listens to those payment events, listens to those, let's say, renewal events that are coming up, and is able to essentially compute from that what the current status of that user's account is. CQRS is a straightforward way for us to implement that by simply updating a flag in a SQL table if we want to. And when that flag gets disabled, next time that user logs in, they're going to be prompted to basically add new billing information, and that's that. We can go ahead and make that part of our application experience very easy and very separate from, let's say, the double entry accounting system we might go ahead and use for keeping track of payments, credits, and debits against their system. So the next part of our high optionality programming, let's say recipe, is talking a bit about actors. So far, we've been very focused on events, persistence, and the way we go ahead and create read and write models. Well, we haven't really talked much about application implementation concepts yet. How can we go about introducing optionality into our software by the way we build it? Actors are a great way to introduce some optionality into your system for several reasons. The first is that they give us that location transparency I was talking about earlier. It's very easy for actors in one process to communicate with another without you needing to know or explicitly address which is which. That's all built into the actor reference system that Akadonit uses. Next is that actors have the ability to take a giant fire hose of events. Let's say you have our big web API from earlier, and that web API, the way we've decided to make it work, is it's going to go ahead and automatically convert that HTTP request into a command that we're going to send into our actor system, and actor is going to process it and send a reply back. Well, if you go ahead and think of the stream of all events hitting all of your different instances of your web API, that can be a pretty big fire hose of data. At my last company that I mentioned in our previous video, Marked Up, we were having 4,000 or 5,000 events per web server per second during peak hours. We can go ahead and use the actor model to break that giant stream of events up into lots of small, easily identifiable streams where each stream belongs to, let's say, a single entity inside our system. So in Marked Up's case, each entity might be a single user of a single app. And then we might have a campaign for several campaigns for each user. The actors give us the ability to partition that data dynamically if we want to, meaning we can redistribute where work happens as it's being processed. So we don't necessarily have to have, let's say, a hard-coded addressable way of referring to this node for this user or this node for that one. We can go ahead and make it more dynamic and respond to, let's say, changes in our topology. This gives us the option of being able to introduce horizontal scaling to our software if we want. That's one of the big benefits of cloud computing in the first place, is the ability to scale your software linearly with demand. That gives us predictable cost control and makes it easier for us to avoid problems like single point of bottleneck and single point of failure. Now, on top of that, the actors also give us a very reliable sort of unit of work pattern to process events in real time. We have the ability to go ahead and do things like have this actor change its state while it's processing those events. And as our domain gets more complex, we could do things like introduce new behaviors, or we could even introduce new actors we can delegate work to without having to bring the system down in order to do it. We can go ahead and just deploy a new instance of the process. The process can go ahead and continue handling the same events as the older ones, but the underlying implementation details can be different, unbeknownst to the other nodes inside the cluster. This is one of the key facets of what makes Akka.NET attractive to CTOs and other companies that are deploying Akka.NET solutions into production. Let's talk a bit more about how they actually give us some optionality. So first, they're a very common way to implement event-driven programming. We've already talked a lot about how that gives us options that we didn't have before. But on top of that, one really powerful feature that actors give us is the ability to make our live application state queryable at runtime. Meaning I can go ahead and query all of my actors that are running right now and say, give me the current state of this entity, or tell me about the most recent 5 messages you processed, depending on how you program it. And this is an extremely useful feature for debugging complex systems or systems that have to operate at very low latency. The next big option that actors give us is the ability to make stateful server-side programming a viable option for us. If you want to build a low latency application, you basically have to do this. There's not a feasible way of doing a stateful database-driven development application. You're just not going to pull it off. I've got an entire presentation I've given on it that's live here on YouTube. Believe me, I've tried. It doesn't work. So stateful server-side processing makes it possible to introduce all sorts of low latency programming scenarios. It makes it possible to build things like multiplayer games quite easily. And it's really a arrow in your quiver you would like to have. And using actors in the right places inside your system, where let's say you're dealing with parts of your application that have to be highly available and low latency, that'll go ahead and give you a lot of choices you can leverage on how you want to go about modeling that exactly. Now, the other options that actors give us is they can make event processing dynamic. I've talked a little bit about actor behavior switching. That's one example of that. But also message routing and distribution are another way they can do that. For instance, in Akka.cluster, we have what's called a weighted router. This is from the Akka.cluster.metrics library. It allows us to go ahead and decide, I want to route this message to the node with the least busy CPU. And that way I can go ahead and essentially distribute work from nodes that are busy to ones that are not. So this tends to work very nicely alongside technologies like auto-scaling, for instance. That's a very dynamic way of processing requests. Whereas in a RPC / let's say web-centric system, the web server that receives the client's request has to be the one that replies back to it, because that request is physically tied via a shared connection to the server that received it. And that's true even if you use technologies like WebSockets as well. Whereas this process of event processing can be very dynamic inside an actor-driven system. And then finally, actors make it possible for us to partition, parallelize, and distribute state with no code changes. This is inherent with how, let's say, actors go ahead and distribute events by either looking at their properties or by taking a look at the load on the system, or maybe it might be as a result of other events they've previously processed. So actors give you a lot of powerful tools for being able to change how work is done at runtime. And you can change those rules between deployments without having to execute a major refactoring of your entire application. They give you a lot of that flexibility from the very beginning. This is what we're talking about with high optionality programming. It's building these options in from day one. Now, the final bit of content I want to cover here is extend-only design. Again, I just did a big video on this about a week ago. Extend-only design is a great way to go ahead and make sure that we don't accidentally destroy value and create technical debt by making it so we lose data, or we have to go ahead and rewrite our entire application each time our schema changes. The idea behind extend-only design is that previous schema that's been used for storing data inside our application is essentially not open for certain types of modifications. In particular, we can't change the meaning of any fields, nor can we delete any existing ones. So schema, wire formats, and APIs are all frozen. New properties, new event types, or new schema can always be added, but old properties can never be changed or removed. As your system evolves, you can gradually stop using old schema, but you can't delete the ability to deserialize and use it because you might have old events or old clients that still use it. Where extend-only design originally comes from is actually from managing file formats in the 1980s, but then the next big leap that it made was for managing SQL Server schema. Extend-only design works very well in that universe as well, since it allows you to introduce changes to your schema independently from when you introduce changes to your application. You can deploy your schema change first because that schema change doesn't have any negative impact on any of the existing schema that's already there, per the rules on screen here. So this is from my previous video that I also shared, but here's an example of what extend-only design looks like using a protobuf message, where I have this ask message, and I go and introduce this new property. This won't break wire compatibility inside my system. If I go ahead and introduce my new library with this new version of the event, and I go ahead and distribute that event over the network, all the nodes that see this new property that they don't recognize will simply ignore it and just move on. So we might have a bit of data loss there, but we don't have, let's say, a giant destructive change that requires me to do a database migration and roll out my application concurrently, which, by the way, if you still deploy software that way, that's really dangerous and you should stop. With this approach, I have the ability to get backwards compatibility as well, where let's say if I have a node that sends me an older message that doesn't have that property, I'm going to go ahead and just substitute a default value, which could be null, or it could be some other meaningful default like false if I'm using a Boolean. So I can go ahead and make sure that my new software has the ability to still interact with older versions of it while we're in the middle of doing a deployment, or whether we're reading old events out of a database without breaking it. So let's talk about extend-only design and optionality. So the whole idea behind extend-only design, preserve old schema, but allow new modifications to be introduced. The biggest benefit we get from this from an optionality standpoint is that our application is no longer tightly coupled to the new changes in our schema. There's no need for things like live schema migrations as part of our deployment process. And more importantly, there's no downtime either. New events can be introduced without causing negative consequences for existing versions of the software and vice versa. It gives us a lot more flexibility around how we do deployments and also helps make sure that we preserve data safety over a long period of time. So old schema is always viable under the system as well. There's no need to do a schema rollback, which is one of the most terrifying concepts in software development I've ever seen, that you could unapply some schema change you made because the old version of the application can't support it, and there's some problem with the new version of the app as well. You're going to end up destroying data if you do that. Whereas with extend-only design, any new data that was saved using the new format, even if you roll back the app, it just sits there at rest. And the old application will, or the old version of your application will simply ignore those properties. And finally, you get the option to have zero downtime deployments. You don't have to take the application offline, roll out your schema update, and do a VIP swap. The whole idea of making breaking changes to your schema is terrible in the first place, and you just shouldn't do it. Extend-only design is really like the strongest way to go ahead and help guarantee that it can't happen. So it gives you a lot of flexibility around how you do deployments, helps keep your old data safe, and gives you the ability to go ahead and evolve your system over time. Now, it's not going to help you with things like migrating to another database necessarily, although in theory, with a really simple event sourcing scheme, I guess you could. Would be relatively easy to port that, but it gives you the ability to go ahead and decouple when your application is deployed from when the schema that it needs is also deployed as well. I mean, in broad strokes anyway. You don't have this sort of tightly coupled, both of them to be deployed concurrently at exactly the same time. Typically, the way people do it is you can roll out your schema changes well in advance of when you deploy the application that uses it. And that's kind of the safe way to do it. So let's go ahead and wrap up. High optionality programming, what are all these patterns that we've shown you? What do they all have in common? Well, the really big properties that give us optionality are all of them encourage immutability. Events are immutable. Schema's immutable. The state that our actors go ahead and send back and forth via message passing is immutable as well. So we don't destroy or change the past meaning of data. That gives us multiple ways to go ahead and reuse it in the future because its original state as it was written is still there for us to leverage in new and different ways. That gives us a lot of freedom and options that we wouldn't have if we used an object store where every time you go and modify one of its properties, you're erasing the past values of that data. Next is we get conservation. High optionality programming tends to err on the side of preserving past data and perpetuity for future Conservation of data is the next property. High optionality programming errs on the side of preserving the past and perpetuity for future reuse. This is what allows us to do things like new projections or simulations or being able to run predictive models on top of old data. That's a very powerful tool that allows us to know if our new changes are going to be safe and helps avoid having to make lots of painful, let's say, restructuring and testing around there to try to guarantee that. On top of that, it gives us the ability and the option to reuse that old data in new ways without changing its meaning. This is what CQRS and event sourcing in particular really help us do. Finally, we get a lot of dynamism out of high optionality programming, the ability to dynamically route, process, and react or update state with ease. This is what Akka.NET and event-driven programming really help give us. The ability to go ahead and make sure that we can scale the size of our system, we can delegate responsibilities, and we can go ahead and essentially move areas of our code around between services without it being a gigantic refactoring project. That built-in dynamism these tools give us, that option to do this in a much less expensive way than what you'd get out of a traditional HTTP-centric sort of microservice architecture. Then finally, we get separated concerns. Each pattern addresses different facets of modern software. So you have the event-driven system for thinking about your sort of API surface area. You have actors for thinking about processing it and handling and reacting to it. You have your event sourcing for thinking about how to make those actors reentrant and redistributable over the network. And you have CQRS as a sort of a way of thinking about how can I take this relatively simple write model and turn it into the more complex read models I might need to support my end user expectations. For instance, I need to have some way of taking the output of these events and the state these events are used to produce and making that indexable so users can do full text search. Well, CQRS helps you do just that. It gives you the ability to use the right pattern for representing data the right way. So you don't end up coupling unrelated models together. Your read and write activities can be designed for their own purposes using the best tools and practices available for each. So that's one of the other big ideas behind a high optionality programming is keeping our concerns separated from each other so we don't try to use one tool for 4 different things, only one of which it's any good at. So to recap on high optionality programming, let's start with technical debt again. It's caused by the destruction of future viable options, usually just through not thinking about how software is going to evolve over time. You might think that a repository or maybe an event-driven programming model is a useless abstraction today, but then whoever inherits the software system from 5 to 10 years from now, maybe that might even be you, might run into a situation where you need to change databases because you're running into some problem that you can't really resolve with the current database architecture, and now you find you don't have the ability to do it. Thus, it's going to turn into a gigantic, expensive refactoring project that could have been prevented. The alternative is to adopt a high optionality architecture, which requires you to pay an upfront premium because typically these patterns we've introduced usually require a little bit more planning, learning curve, and thought ahead of time versus the defaults a lot of developers use. But high optionality programming is something you should absolutely desire inside your system unless you're really certain your requirements won't change. And as an experienced CTO and software architect, I'll tell you that if you're betting that your software won't change, you're probably wrong. So you should plan on evolution being an inevitable factor in your business and your software over time. And optionality is something that you should start introducing in your design conversations very early. So hopefully these 2 videos really helped you get a handle on how to go about doing that. If you're interested in having a member of our team from Petabridge work with you to help you design some high optionality architectures of your own, please go ahead and go to our website, or I'll include a link to a specific page you can go to request our help down below, and would be happy to help you with this very much. So thank you for listening, and please don't forget to like and subscribe. Thank you.